We'll start this presentation with a review of key points from the first two classes on climate change. We'll need to put all these pieces together to explain how and why climate change is occurring. Recall that a black body is a hypothetical material that absorbs all radiation incident upon it. It doesn't reflect any radiation. Physicists tell us that black bodies emit a spectrum of radiation where the peak wavelength is inversely proportional to the temperature. So cooler objects will emit radiation at longer wavelengths. The Earth behaves mostly like a black body, and at its surface temperature it emits radiation with the wavelengths in the far infrared range. The Earth is effectively glowing out this infrared radiation. We just can't see it because our eyes have evolved to only see visible wavelengths. The Sun is a lot hotter than the Earth. So according to Wien's law, it emits with a peak wavelength that is much shorter than the far infrared of the Earth. About half the energy coming out of the Sun is at visible wavelengths. The Sun also emits at ultraviolet wavelengths, shorter than visible light, and at infrared, longer than visible light. To summarize the last two slides, peak wavelengths coming out of the Earth are infrared. Peak wavelengths coming out of the Sun are visible light. The other key pieces from the last lecture that we need to describe climate change are that when the material interacts with electromagnetic radiation, it can happen in two ways. The radiation reflects off the material, or it is absorbed by the material. Note there's a third possibility in this diagram, that the EM radiation will just pass through the material, in which case we would say it is transmitted. But we don't need to consider that here because the EM radiation coming off the Sun is either reflected or absorbed by the solid Earth or our atmosphere. Another key piece, when radiation reflects off of something, that thing's temperature doesn't change. You can think of it as all the energy that the radiation brings in also just gets reflected back out. So none of the energy goes into the thing that is causing the reflection. When radiation gets absorbed, that's different. The energy in the radiation goes into the thing doing the absorbing, and that thing heats up. Gases can absorb electromagnetic radiation, but unlike solids, can only absorb waves with specific wavelengths. The Earth is a solid that behaves similarly to a black body, meaning that it absorbs most of the incoming radiation at all wavelengths. But above the Earth's surface are the atmospheric gases, which only absorb at certain wavelengths. Now we'll put these ideas together to see what happens when the electromagnetic radiation from the Sun reaches the Earth. You can see from this diagram that about half the radiation is absorbed at the surface of the Earth, about 30% is reflected, and the rest is absorbed in the atmosphere. There's another way to describe these numbers. The Earth absorbs about 70% of the incoming solar radiation, and of that 70%, about 1/3 of that absorption takes place in the atmosphere. Here we see the spectrum of the Sun that reaches the Earth's outer atmosphere, shown in yellow, versus the spectrum that's seen on the ground, shown in red. You can see that huge chunks of the ground radiation are missing, corresponding to portions of the spectrum that have been absorbed by gases in the atmosphere. The difference between red and yellow is due to absorption by gases in the atmosphere, which happens only at specific wavelengths. Notice that the shortest wavelengths in the UV band are completely absorbed by the atmosphere. This absorption of the shortest UV wavelengths occurs in the stratosphere. The atmosphere has two layers relevant to climate change. There are higher layers defined by scientists, but the two that matter for our discussion are the troposphere and the stratosphere. The bottom layer is the troposphere. The troposphere extends from the surface of the Earth up to about 10 miles or 16 kilometers. Airplanes fly at around 10 kilometers above the surface, within the troposphere. The stratosphere is above the troposphere and extends upward from 10 miles to about 31 miles, or 50 kilometers. The Mickey Mouse on the right is a diagram of an ozone molecule. It's just made of 3 oxygen atoms bound together. The ozone in the lower stratosphere absorbs radiation in UVB and UVC wavelengths, so very little of the UVC emitted by the sun makes it to Earth. This is good for humans because UVC is the shortest wavelengths, so the most energetic of the UV band radiation, and causes skin damage and cancers. You may hear in the news also about ozone as smog or air pollution. This, quote, bad ozone is formed by the interaction of sunlight and the emissions from cars and smokestacks, and may be concentrated around congested traffic and factories. People with respiratory problems suffer in zones of high ozone. So in summary, ozone in the stratosphere is good. It absorbs UVC and protects us. Ozone in the troposphere is bad for our lungs. Remember, the Earth also emits radiation, but at longer wavelengths than the sun, because the Earth is colder. So the next piece needed to describe why our climate is changing is to understand how and why the Earth emits its own electromagnetic radiation. Here's another example of a human emitting radiation as measured by a camera sensitive to infrared wavelengths. What would this image look like for the whole Earth? Recall I said earlier that objects with temperatures around that of the surface of the Earth emit far infrared radiation. And that the colder an object is, the longer its wavelength and the less intense the radiation. Here's a diagram showing the Earth's radiation spectrum compared to the sun spectrum. To summarize, the sun and the Earth emit radiation at different wavelengths. Even in the infrared band of wavelengths, the sun emits in the near infrared, while the Earth emits in the far infrared. The two spectrums don't overlap. Different kinds of life on Earth have adapted to use different wavelengths. Humans have adapted to use the intense visible light emitted by the sun. In contrast, nocturnal animals have evolved eyes that are sensitive to infrared wavelengths. Anything on the Earth's surface is emitting infrared radiation, the land surface, other animals, etc. And they radiate this all the time, both day and night. So these animals with infrared detecting eyes can see during both day and night. It's interesting that humans have adapted to use the more intense light that comes from the sun, but that light is only available during the day. Here's a mouse as seen by an infrared camera. It appears as a bright spot because it is warmer than the ground beneath it. Remember the Stefan-Boltzmann law: if something is warmer, it emits with greater intensity. How convenient for the lizard. An infrared image of a house shows the red areas that are emitting the most radiation because they are the warmest. The walls are warmer than the roof. So think about this question at the top of the slide for a minute before you hop to the next slide. The thermal imagers that sense infrared wavelengths, are they using the physics of the Stefan-Boltzmann law or Wien's law? The answer is the Stefan-Boltzmann law, which says that material at higher temperature emits greater amounts of radiation.